everybody. We are now in the final chapter, chapter 25 today of the book that we're going to be doing this year for the AP. So we're going to run through this today because it is a lot of things we already know, but we're going to be talking about paired data. So you're going to be able to determine whether two groups of data are independent of each other or paired. And this independence thing, we're finally going to see actually the first time that we're not going to have something independent, but rather paired, and that's okay. So let's look at the example they use throughout the book, and you're more than welcome to read the book as well. But they're talking about how speed skating, you're running pairs. I'm sure you know that, is that they put them side by side. They're actually obviously staggered because one person in the middle is goes quicker. And then they start at the same time, one inner lane and one outer lane, and then halfway through they cross over. And if you've ever been in this type of race, you also know that the person that is pushing in the front usually pulls the rest of the group. It usually is like fast heats, they call it. People are trying to keep up with the person who's the fastest. So you usually want to be in a heat. Sometimes, it depends. It depends on whether they're taking it by heat or taking it by total time. In any case, they actually had inner lane, outer lane, and they're actually saying that these are not independent. And they're not independent because the assigning of the skaters, even though that was assigned randomly, probably at some point in the Olympics, the comparisons, the conditions of the track, etc., will actually dictate whether or not there's pairing or not. So each group together gets paired together. I don't know how often they bring out a Zamboni. I'm imagining it's not every single time, maybe every fifth time, maybe every 10th time, maybe not at all. I don't know. But they are paired because each grouping is timed together. So what is paired data? So data are paired when the observations are collected in pairs, or if the observation in one group is naturally related to the observation in another. The most common way we see this is called before and after. Okay, so anytime you have something before and after, weight gain or loss, a diet, some sort of tracking of mileage, those would all be considered paired. So pairing in an experiment is called blocking, and pairing in an observation is called matching. Remember, matching and blocking are the same thing, but one's matching is for observations and experiments is for blocking. That's a good review for 2 weeks from now. If you know the data is paired, you must take advantage of that. And just deciding that it's paired, you're going to think about the whys. Why are we doing these things? Checking the W's, which we did way back when in September. There's no test to determine pairing. And once we know it is paired, we can examine the pairwise difference. Because it's the differences we care about, we treat them as if they were the data and ignore the original two sets. So what we're going to be doing is we're going to be taking the two sets of data and subtracting them to find the difference. And the difference is what we're going to use for our calculations. Okay. So before we move on, I'm going to go through a few quick questions, and you're going to look at them and you're going to determine whether or not it is paired data or not. First one. Company institutes an exercise break for its workers to see if it will improve job satisfaction. My husband actually works for Swiss Re. I don't know if any of your family works for them. They're pretty big down in Armonk. And they have some people in New York where he used to work joke that it's the country club because they have a workout room, they have tennis courts, they let you go run at lunch. It's really nice. That's a nice perk. So he actually can go to spin class. He has to sign up in the morning to go at lunchtime to spin, which is kind of fun. Anyway. They're assessing job satisfaction scores for 10 randomly selected workers before and after implementation. They want to know the effectiveness of the exercise program. So, is this paired data? Yes or no? The answer is yes, it is paired data because it's before and after. They're asking for the job satisfaction out of whatever the number is. I don't know, is it out of 50? Is anyone higher than 50? Is it out of 50? It doesn't say. So we'll say it's out of 50 job satisfaction. So people are, they're comparing the exercise program before and after. How about this next one? Having done poorly on their math final exams in June, think about the Regents, 6 students repeat the course in the summer school, and they take another exam in August. If we were going to consider these students representative of all students who might attend the summer school program in other years, do results provide evidence that the program is worthwhile? Is this paired data? Yes, it is, because we're still doing before and after. Same student, June, same student, August. So it is still paired data. Okay, so that's where paired data would come into play. I have one more example. Give me a second. I have it all the way down here. Where is it? Is this it? No, that's not it. Is this it? Yes. Every year, students take a physical fitness test. One component is they have to do as many push-ups as they can. They have the boys and the girls push-up amounts. And is this paired data? No, it is not, because we have boys and we have girls, and they're just doing their push-ups. If I have a friend in front of them counting, and that's it. There is no pairing of groupings. There is no before and after. It's just the boys and the girls, okay? So this would be a traditional, what we're seeing in front of us, the push-ups, a 2-sample t-test, or a 2-sample t-interval in this case, in this example. The other ones where we're going to be doing paired t-intervals and paired t-tests. So where am I? I'm back here. Let's look at this one. Do flexibility schedules reduce the demand of resources? So they're saying that they're trying to implement a 4-day work week. They're talking about the miles driven by field workers, people who have to go out in the field, whether they're salespeople or whether they're fixing things or whatever. And they have to check on their mileage. So is this paired data? Yes, it is, because it's before and after. Jeff, 5-day mileage. Jeff, 4-day mileage. Okay. So that's what you have to do every time. Take a look at the 2 pieces of data. Is it paired or not? I will tell you, we're having a full-on chapter on paired data. It's 1 day. So I would think it's not going to come up that often. If I saw 2 pieces of data, my first thought would be a 2-sample t-test or t-interval. However, yes, there's a chance it could be a paired t-test as well. So what's going to happen here? Let's talk about the mechanics. Now that we have only one set of data to consider, we can return to the simple t-test. So when we're doing a paired t-test, we're going to use on our calculator the button t-test. However, on your paper, you're going to write paired t-test. Mechanically, a paired t-test is just a 1-sample t-test of the means of the pairwise difference. The sample size is the number of pairs. So in this case, we do know the degrees of freedom because it's going to be n-1. So let's talk about the assumptions and conditions. Most of them are the same, but here's the one that's going to be really important and different is the paired data assumption. You're going to say that it's the paired data assumption has been met or something like that. You're going to look for independent data, the independent of each other, still out there. It still has to be random. Or if we're talking about a representative, when we're talking about the people working in the company, the field workers. 10% condition. When the sample's obviously small, we may not especially check this condition, but so less than 10% of the population. And then nearly normal. This one's also a little bit different. We're going to be checking the plot of the differences. So instead of doing a side-by-side comparison of the 2 pieces of data, we want to know the differences. It's also super important when we get to that point because if we had a student that got a 50 in a class and then they got a 75, you want to keep those 2 people together. You don't just want to care about the whole piece of data. So I'll show you examples of graphs when you don't do the difference and how that's going to affect your analysis. So I am going to jump to other things, and then we will go back to an example. Paired t-test. So when the conditions are met and we're ready to test whether the paired differences differ from 0. So we're going to do a null hypothesis for the mu d. It's not 1, it's not 2, it's mu d. D being difference, where the D is the pairwise is difference and the delta is almost always 0. So I would do, in the case of the, if I'm looking to see if there was a difference in the field workers and whether their mileage went up or down, because don't forget, it could actually go up because they might be bopping around all around the county versus saying, I'm going to go to one town for the day and then another town. So they might go from like Bronxville up to Yorktown and then back down to Scarsdale or something, versus saying, I'm only going to stay in Yorktown for the day. So the alternative in that case, they're looking for difference. It would be mu D is not equal to 0 or greater than or less than, depending on what you're looking at, okay? This test statistic would be the T critical value would be the mean difference minus the change, which would be 0, over the standard deviation. We're not going to have to calculate this. They're going to give us the data, or they're going to tell us the numbers, and we're going to plug it into our calculator. We're going to use that to find the T value, to find the P value, and to find the degrees of freedom, which is n minus 1. We can also do confidence intervals for matched pairs. Same equation. We're seeing the same thing. In this case, it's going to be, instead of being the P, the probability, or the mu, it's going to be D, the average of the D. And the critical value, of course, we're going to calculate from our calculator. This is the picture I was telling you about. If we looked at the data side by side, in this example, we're looking at husbands and wives and their age differences. So in the left side, it has wife, it has the right side, it has husband. And if you notice, they almost have the exact same mean. They almost have the exact same max and min, which this min is kind of weird. I hope that's 20 and not anything smaller, maybe 18. I don't know. Anyway, but I have no idea whether the 18-year-old wife married a 60-year-old man, or whether a 45-year-old man married a 6-year-old woman. I have no idea from this graph. So that's why we have to do only looking at paired data, looking at the difference in the data, and then we do a histogram, or we could do a box plot too. But the histogram will then give us to see nearly normal, unimodal, and roughly symmetric. Okay. So pairing removes the extra variation we saw in the side-by-side box plots and allows us to concentrate on the difference. And paired design, as we just talked about before, is blocking. So let's do an example together, and then we'll be done for this chapter. So this was the example of the students that had to repeat the course. And I'm going to start with create a 95% confidence interval of how much better the students did in August versus in June. So let's go follow along with your calculators, please. I'm going to go to my calculator. I was playing around with some other problems too, but I don't think we're going to do them today. So I put my data into L3, L4. You can put yours into L1, L2. I made my L3 June and my L4 August. So now what I'm going to do is I'm going to go over to my L5, and I'm going to do, I can see that they did better in August versus in June. So I'm going to do August, which is going to be second for me, second L4. Yours might be L2 minus L3. So I'm taking the August minus the June. In this case, L4 minus L3. I do it on L5. Please practice this because this is going to be kind of tricky. And I'm going to hit enter, and there's my differences. So now what I'm going to do is I'm creating a 95% confidence interval. So I put the data in. So let's now talk about our panic. That's right, panic. So panic is going to be I'm going to write the mu delta, the mu D. Sorry, I keep saying delta. The mu D is going to be the difference between August minus June scores. Okay, so let's talk about the assumptions and conditions. These are 6 students. It does not say, it says it's representative. So it's going to be representative. Oh my gosh, what am I writing? of students. They are independent of each other. It's less than 6% of the population, less than 10%. The nearly normal condition, we're going to do it right now. I'm going to write nearly normal, and I'm going to write why it's nearly normal, if it is. I'm going to go now to second stat plot. I'm going to turn on my stat plot. I'm going to do a histogram, and I'm going to do it for my L5. Yours might be L3. Mine's L5, okay? And I'm going to hit graph. Oh, I got to get rid of Zoom 9. Zoom 9. And I have a data of grid. Now, the problem is, as we know, is that I only have 6 pieces of data here. So the graph has blanks. That's okay. I can still see that it's unimodal and it is roughly symmetric. Nearly, so it's unimodal and roughly symmetric. So yes, it's nearly normal. So the last thing is paired data. It's paired data. And I'm going to write down how I know that. It's before and after. It's before and after. Okay. So therefore, use paired. I need you guys to write paired t-test. You have to write that down, even though on your calculator you're using a t-test, because the calculator it's the same exact equation. So that's fine. The same exact calculation. So let's go now, panic N, we name the test. Now we're going to do the interval. We name the interval. We're going to go and do the interval. So let's go to stat, tests. We're going to do a 1 sample t interval. Right here, t interval right here, number 8. Make sure I'm doing data. Make sure I do L5. In your case, it'll be L3. It asks for a 95% confidence interval. And then enter. So I'm at 52 to 57. And we have, I just want to make sure, did I do L5? Now I'm nervous here. Stat, because the number should be, what did I do here? What did I do wrong? 8. I did L3. See, aren't I glad I caught that? I hope you guys caught it too. L5. I even said L5, didn't I? L5, stat, tests, 8. L5, 95% confidence interval, and calculate. Okay, get -2 to 13. Okay. -2 to 13. So what am I going to write as my final conclusion? We are 95% confident that the difference between test scores from August to June is -2 points to 13 points. Interestingly enough, you know my next question is going to be, confidence is spelled wrong. Okay. We are 95% confident that the difference between test scores from August to June is -2 points to 13 points. So it actually went down or it could go up. And we saw that from some of the numbers. So my next question, I'm going to ask, is there, and this was the original question, is there evidence that the program is worthwhile? So let's tweak this, what we just did. So I still have my data in there. We're going to use mu d is going to be the difference between August minus June. Okay. Let's do our hypothesis test. We're going to do HO. Let me put the little dots. Mu d equals 0. And HA, mu d, is greater than 0. We want to know that it's worthwhile. Is the program worthwhile? Did kids pass? I think we have an idea what it's going to be. We already met the assumption conditions, assumptions and conditions. So what we're going to do now to do evidence is a test, we're going to do a paired t-test. Did I call it a paired t-interval? I feel like I called it a test. This should be interval right here. Sorry. Hopefully you guys were following along and realized that. Oof. Okay, paired t-test. So now let's do this. So we just did, this is phantoms. So PHAN, name the test, T, do the test. So let's go to here, and we're going to go to stat, tests, and we're going to do a t-test. Even though it's a paired t-test, we're doing a t-test. Make sure you're on data. Mine is still defaulting to L5. My mu is 0. And I'm going to do that it is greater than. So because I want to see it be greater, I want to make sure that there is evidence. So I get a t-score of 1.75. Oh, let's name the alpha level equals 0.05. Okay. So let's write down some of the things. We got a t was 1.7. Did I say it was? 1.75. The p-value was 0.067, I think it was. It's 0.069. I'm going to leave it 0.699. How about that? And the degrees of freedom, as you can imagine, is going to be 5. It says 6 there, n is 6. So we're going to have degrees of freedom equals 5. Okay, so let's do we obtained O, the p-value. We're now going to make a conclusion. Since the p-value of 0.0699 is greater than the alpha level of 0.05, we fail to reject the null hypothesis. Oh my gosh, who is this? There is no evidence. Okay, what is it? There is no evidence that the program is worthwhile. What is worthwhile in this example? That August scores were higher. How did we know that even without doing this? Because our confidence interval had 0 in it. That's how we knew that. Okay. But this hypothesis test, when I say the word evidence, I need to do a test. Okay. That is it for me for today. That is it for chapter 23. Don't forget, we're going to have a test on chapter 25. Chapter 23, 24, 25. This finished chapter 25. We're going to have the test on Tuesday. We will do review on Monday. Have a wonderful, wonderful weekend, everybody. Bye now.